The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and welcome to this live learning event entitled Choose Wisely, Cement Grout, Chemical Grout, or both. My name is Don Rigby, Director of Marketing for Avanti International. Today I have the greatest job in the world. I get to introduce you to some pretty savvy people and facilitate a session to maximize the next 59 minutes for you. Not all grouts are created equal. Each are engineered to produce with unique properties to provide specific attributes for both new construction and rehabilitation projects. Which one, how long, how much, and why? You'll learn directly from our panel of experts who have devoted their professional lives to this industry and enjoy teaching what they know so others can do. The platform we're using has all participants on mute, but it's important that we get interactive. And here's how we get it done. You're going to have questions, and that's a good thing. We'll reserve time at the end for Q&A, but I recommend as questions come to mind, immediately type them into the collapsible dialog box on the right-hand part of your screen. In fact, I suggest you look at that and view that momentarily, if you would, please, so you know when to submit questions and how to submit them right away. It may be that I would interrupt the speaker and ask right away, or I may choose to reserve it to the end. But if we don't get to all these questions in the webcast, we'll certainly answer every question individually by mail, and that's a promise. I'm also a clock watcher because I respect your time. I'll do my best to end this session in 60 minutes, so you'll feel good about joining us in future webcasts. And one last bit of information. There will be 3 interactive poll questions asked during the session. These are very interesting because I get to play back the answers right away. So let's do the first one right now. If I can multitask, I will launch the very first question and ask for your participation in answering this question. I get to see the voting and how it's coming across, get a sense for, actually, I don't get to see who's coming across. I'm hoping that, there we go. Yeah, I got a small percentage voted. Please take the time to complete this. And it looks like we have a very, very good showing from Public Works. I will close this in a moment. And I'll share. And from this, you see a very good standing of folks in the public works profession. Thank you for that. I'm going to hide this. And take the moment to introduce who our experts are today. Sam Bandemir is an independent grouting consultant and a founding member of the annual Colorado School of Mines short course, now in its just completed its 34th year. Welcome, Sam.
Good to be here. Thank you.
And Brian Jepson is Vice President of R&D at Hess Pumice Products in Idaho. U.S. Grout is one of Hess products, and Brian is responsible for testing this product in unique and challenging environments. Is that accurate, Brian?
That's accurate. It's great to be with you today, Don.
Awesome. And Britt Babcock. He's an engineer and heads up the geotechnical division for Avanti International. He's our road warrior. He spends half of his time on job sites with contractors and the other half with the engineering community on job specifications for both chemical and cementitious grout. Britt, thank you for being here.
Thank you.
To start us off, I would like to ask for Sam to lead a session here to begin this knowledge share with a session called What Problem Are You Trying to Solve? And I will make you presenter, Samuel, and ask that you acknowledge and take off from here.
Okay. Okay, well, I think it's first and foremost important to understand that grouting really has 2 applications, that being the geotechnical applications and the structural When we look at structural, you're usually dealing with cracks or honeycombing or some type of repair in concrete, whereas the geotechnical, you're dealing with some type of a soil or rock application. When we look at geotechnical, there's a myriad of grouting types that you can use for different applications. And I just have a little chart that I put together here to give you an idea as to what's available out there and how to use them. And I hope that that's helpful. When we look at structural applications, as I say, usually you're dealing with concrete, but you could be doing encapsulation type work, for water cutoff, things like that. Machinery bases, a lot of work done on the structural applications in the grouting industry. We really have three application levels, that being the homeowner level, commercial, and industrial, and I give you some dollar amounts there that kind of break those apart for you. Three types of contracts: time and material, engineered, or a specified type contract, and a design build. And the document that I've submitted for this seminar, Contracting Means and Methods, I hope would be helpful for you to read, and if you have any questions, be sure to submit those in those regards. Well, when we look at grouting, ground modification involves compaction grouting, where we inject a very low mobility type grout that does not enter the pores of the soil, but just simply displaces those soils. And I've given you some equations here to kind of work on how that works, dealing with weight-volume relationships and dealing with low mobility type grouts. And of course, no matter what type of grout you use, you're going to look at, you want to make for sure that you've accomplished your goals. So you're going to need to do some before and after type grouting, CPTs, SPTs, some type of verification work that you know you've accomplished your goals. When we look at ground modification, other applications, you can do permeation grouting, where the grout is designed to enter the pores of the soil and either glue them together or fill those pores, depending on whether you're trying to do stabilization, water cutoff, and so forth. But permeation type grouting is also used. Well, then we also look at cliquage or lens fracture type grouting, where you use very limited volumes of grout to inject and create fractures and intended fractures in the ground to lift things, stabilize structures, and so forth, or to do contact grouting around tunnel linings. Can be doing rock grouting for dams, just trying to fill these very minute fractures, filling of voids, or creating these fractures. Ground modification can also involve soil mixing, where we churn a large auger in the ground and churn these soils around up and inject cements, or could be chemicals, to stabilize these soils, to create some type of a diaphragm wall for stabilization purposes. Well, obviously, water control, a huge market for the grouting industry, and just to show you that there's numerous ways that you can do water control, whether it be with chemicals, cements, low mobility grouts, and when you read that document that I presented, I hope that that kind of helps you understand that sometimes it's best just to let the contractor tell you how he wants to accomplish your end result for you. Releveling of structures, whether that be releveling someone's rear patio on a homeowner market, or releveling a 650-foot tall power plant chimney. It's very important, no matter how small or how large the project, that you know what your grout's doing in the ground. Control of grout is very important, and also to know what you're accomplishing for your end results. For instance, you may, if you're just doing slab jacking work, add a load to a soil that's already consolidating under its own weight. So maybe you need to do some soil stabilization work. But make for sure you know that your grouts are not affecting adjacent structures or structural elements. Waste containment is a huge market in the United States and around the world. And that's done by either soil mixing, permeation grouting, encapsulating hazardous wastes, and that's a very large market for the grouting industry. Dam rehabilitation and even new construction for what dams are being constructed, but usually dealing with rock grouting, concrete injection. But a lot of our dams are becoming outdated in terms of seismic capabilities and so forth. So there's a lot of dam work being done in the United States and around the world today. When we look at below ground structures, tunnels, subways, dealing with confined space, MSHA regulations, a lot of work being done underground, and grouting has a perfect application in a lot of those areas. Seismic upgrades above ground. As you can see from the world map there, seismic occurrences are all over the world, and so a lot of major structures that were constructed before they really realized the effects of these seismic occurrences, and a lot of upgrading being done for seismic upgrades. Well, in my 5 minutes of presentation here, I hope that our conclusions are that grouting is a multifaceted industry. It has unlimited opportunities and certainly cost effective. It's based on engineering principles with experienced choices, but requires a team effort between the owner, the engineer, and specialty contractor. And out of that team, there's going to be choices that are made for project applications and grout types. And the goal is to make those choices wisely, and most of all, to make for sure that we come out the other end with a successful project. So with that, I'm going to turn it over to Brian Jefferson, who's going to talk to us about cementitious grouts and some of their technical properties.
And I've just made you presenter, Brian, if you'll acknowledge.
Thank you very much, and thank you, Sam. We certainly appreciate your grouting knowledge and experience that you bring to this webinar today. Well, folks, I've been asked to take just a few minutes and discuss more specifically some of the basic characteristics of cementitious grouts. And today I'm going to mostly focus on the ultrafine cementitious grout, since that's where I specialize in. Here we have a good visual of a standard sand column test used to demonstrate grout penetration in soil stabilization. This test was performed by pumping the grout solution into the column at about 10 psi for a maximum of 20 minutes. It's easy to see the difference here with the column on the left being regular OPC grout and the column on the right being an ultrafine cementitious grout. One of the primary reasons for this difference in performance is due to the particle size. As we can see here, the ultrafine particle on average is 5 times smaller than standard OPC grout. Therefore, it's better able to penetrate those smaller voids. Here we see an example of how these ultrafine grouts can also be used to successfully penetrate microfractures in solid formations. This is a cutaway example of a successfully grouted salt cavern. By the black lines, you can see these tiny cracks that have been filled by pressurizing the grout into the cavern walls. This is an actual X-ray photo of ultrafine grout flowing through a 7.9 micron opening. To put this in perspective, the finest human hair has the diameter of right around 40 microns. So this constricted opening right here is approximately 5 times smaller than the finest human hair, and yet is being successfully permeated by ultrafine grout.
Fascinating.
Another factor in this ability for a grout to effectively penetrate is, whether it's geotechnical or structural, has to do with viscosity and rheology. Now, contrary to the general public's understanding, the two are not synonymous. A liquid's ability to flow does not always correlate with its viscosity. Viscosity can be defined as a liquid's thickness or perhaps stickiness, whereas rheology is defined as a liquid's ability to flow. Although very near the same, they do not always correlate. Now, here's a simple example of what I mean. We took here just ordinary tap water and ran it through a standard grout marsh cone test. The result was 28 seconds. We then added a common household rinsing agent, effectively reducing the surface tension of the water, and reran the test. This time was 26.5 seconds. Although the viscosity remained the same, the water's rheology, or its ability to flow, was increased by 5%. This becomes a key factor in grouting applications and emphasizes the importance of selecting a correct additive for your specific project. In a great real-world application of this principle of rheology, we recently participated in the sand column demonstration at the Colorado School of Mines Grouting Conference, and were able to achieve a complete 60 inches of vertical penetration in 1 minute and 20 seconds, using a 2-to-1 water grout ratio at only 8 psi. That's a remarkable improvement over past performances and is directly attributable to the change in rheological properties through the additives. In summary, the two main defining characteristics of cementitious grout performance are particle size and flowability. Let's talk for just a minute now about grout composition. Although there are various types of cementitious grouts, most consist of a mixture of Portland or some other type of cement and other various types of supplemental cementitious materials known as pozzolans. In order to illustrate the value of pozzolan, I need to get a little technical for just a minute. The strength and durability of a cementitious grout is derived from the calcium silicate hydrate that is formed as a reaction between Portland cement and water. The more cement you can get to convert to CSH, the stronger and more durable your cement. Without pozzolan, only about 75% of Portland cement makes this conversion. The remainder is converted to calcium hydroxide, which does not add to the strength but can actually be detrimental to the cement. Pozzolans in and of themselves are not cementitious. However, because of their high silica content, when they are finely ground and added to cement and water, they produce a vital chemical reaction which converts the leftover calcium hydroxide to the desired CSH, thereby strengthening the cement and reducing the negative effects of the calcium hydroxide. This CSH conversion process can be continued for decades. These pozzolans can be either man-made byproducts such as slag, coal fly ash, silica fume, or V-cast. In addition to man-made pozzolans, there are also natural pozzolans such as pumice, metakaolin, calcined clay or shale, diatomaceous earth, to name just a few of the most common. For real-world examples of the value of mixing pozzolan with cement, most of us are very familiar with the ancient Roman structures such as the Pantheon we see here, or the aqueducts, which have been in existence for nearly 3,000 years, and of course the Colosseum. In summary, there are several benefits of adding pozzolans to cementitious products, and of course I'm more partial to the natural pozzolan and their consistent performance. So with that, I'd now like to hand it over to Britt to cover some of the characteristics of chemical grouts.
Hey, Britt, I've just made you presenter, if you'll acknowledge.
Thank you, Brian. I'd like to start, we'll talk about the various types of chemical grouts, and primarily there's two families of chemical grouts. There's polyurethane foams and chemically reactive, or solution grouts, if you will. Within the polyurethane family, there's hydrophilic and hydrophobic foams, along with elastomers and urethane gels. And within the chemically reactive or solution grouts, there's acrylamide, acrylate, and silicates. Within the polyurethane foams, the two primary that are used most often are the hydrophilic and hydrophobic. The hydrophilic has a strong affinity for water, likes to be in a wet, moist environment. They typically expand 4 to 6 times and are generally flexible. Whereas the hydrophobic foams have little or no affinity for water, meaning they can withstand wet and dry cycles, typically expand 15 to 20 times, and generally cure to a semi-rigid or rigid state. Here's an example of a hydrophobic foam. This happens to be a single component. So when mixed with water, you'll note that the original volume here, when mixed with water, then once cured, expanded 4 to 6 times. Again, it's primary uses for hydrophobic foams or hydrophilic foams, is water control. They're flexible and they like to be in a wet, moist environment. An example of a hydrophobic foam, this example is a two-component resin. We have component A, component B. When mixed together, again, noting its original volume, its expansion, if you recall, was 15 to 20 times, and obviously this picture depicts that. It's well exceeded the cup's capacity. Hydrophobic foams are oftentimes used to stop water or fill voids. They can withstand, again, the wet-dry cycles and cure to a semi-rigid, rigid state. Whereas the chemically reactive grouts of acrylamide, acrylate, or silicates, they tend to be more of a gel-type component. Here's an example of a mix of two of those. It's the two-component gels. Component A, component B, when mixed together, will form a firm gel. You'll see here in this particular situation, the gel has, the cup was tilted as a gel cured, creating this slope. One of the values or one of the core components of the chemically reactive gels is they're water-based, but one of the benefits is that they have very low viscosity. An acrylamide generally has 1 to 2 centipoise, where acrylates are 3 to 4, silicates are upwards to 5 to 7 centipoise. They also have controllable set times. Acrylamide, for example, can be controlled anywhere from a few seconds upwards to 10 hours. Acrylates and silicates both are within about a 60-minute time window. Here's a quick example of the viscosities that we see representing a table of water being 1 centipoise. Again, acrylamide versus silicates in that 1 to 7 range. The urethanes, the polyurethane foams, whether it's a rigid or flexible, can range anywhere from 50 upwards to 3,000 centipoise. And to put that in perspective, honey has a centipoise of about 3,000 in regards to viscosity. This is a great chart that demonstrates the penetrability, if you will, of the different types of grouts in the industry. This depicts the types of gravels or sands, essentially the different types of soils that may be encountered. And it depicts its ability to permeate into those soils. Cement here being on the far left, being the least able to permeate. This would be just ordinary cement. Dropping down to polyurethanes, then cements or cementitious grouts, if you will, ultrafine, silicates, and then acrylates and acrylamide being the most penetrable into like clay soils. Life expectancy often is a question that comes up. Acrylamide, 362 years. Polyurethane foams are roughly 75 years. Acrylates, 54 years. And then silicates are approximately 2 years. They're generally considered just a temporary solution. Grout cost is also another question that comes up frequently. Now, I want to caveat this slide with the fact that this is supplier cost for the materials. This is not injected costs by the contractor. They definitely are going to have much, or not much, but additional costs over and above this mobilization and their labor and materials and equipment. But this gives it a scale of perspective. Polyurethanes in an uncured state can be anywhere from 60 to 80 gallons. Keep in mind that they can expand anywhere from 6 times upwards to 20. Whereas acrylamide or acrylates, $8 to $10 a gallon. These are mixed gallons, $6 to $8. Ultrafine cements, 3 to 4. Sodium silicates, 2 to 3, or Portland cements, 1 to 2 gallons. And with that, I'll hand it back over to Don.
Well, what I'd like to do is ask that we respond to one question that came across the transom. I think it's best that Brian answer this one, and I think it's, let's talk about the, what is the window of workability of cementitious grout?
Depending on the application, you typically have 2 to 4 hours before it hits its what we call the initial set, which is when its workability is, pretty much expired. So I'd say about 2 to 4 hours.
Good. Any other questions? I encourage you to submit along the way so that I could have a good cross-section of questions for the panelists at the end of this session. Or, again, I may choose to interrupt and ask to respond right away because I'm monitoring these things very closely. I'm going to launch another poll question. This was just out of curiosity, and I'd like for you to share with us what your level of experience is with cement or with chemical grout. And I'll let you look at that and decide where you best fit. And I'll keep an eye on the number of people who have voted and see that process. I encourage you all to participate in this. Thank you. Got about 60% of the vote in, 86%. I think I'm going to close the session, this question now, and I'll share it with you all. And it's looking like the majority of our audience is anxious to learn more. Well, you've come to the right place. I am going to close this out, and I will ask that Sam then take on the second part of this session. And Sam, if you will present next, I would appreciate that.
Okay, thank you, Don. Well, as we continue to look at some of the technologies and methods of placing grout, some of the talking points, we're going to be talking about pumps, grout delivery systems, probes and casings, monitoring methods, grout packers, and sleeve pipe injection system for getting our grout placed to its final destination. When we look at pumps, you're dealing with piston pumps, cavity advancing pumps, diaphragm, parabolics, and the size of these pumps is going to vary depending on what you're doing and the size of the project. But it can be anything from a modified concrete pump to a little hand pump that you just do maybe door frames with or something. But just a myriad of pumps that are available out there to place these grouts with. Well, other delivery system requirements is rubber hose, and of course when we're looking at hoses and so forth, we need to look at proper clamps, whip checks, and proper gauge transducer protections so that you don't get your grout into your gauges and transducers. Also, you need to look at your burst pressures, look at safety issues on these delivery systems. Just a word of wise there. Well, grout probes and casings. These are usually the final delivery elements that place the grout where you want it, and so they can be made of steel, plastic, copper. The ID of the casing or probe must accommodate the type of grout that you're pumping. Obviously, if you're pumping an ultrafine or a chemical, the ID can get rather small. If you're dealing with a low mobility grout, you're probably looking at casings with a minimum ID of 2 inches. But in any case, you need to look at your reaction forces from the ID of your probe because there is a reaction that can push that casing or probe right back at you. It basically becomes a jack. So you need to look at your casings and probes for some of those issues. The length of your probe or casing is going to vary. If you're in a confined space situation and you've got to place your grout a fairly good distance away from the structure, you're going to deal with very short, small lengths of casing that can be screwed together and sent through the structure to get the grout out there. If your overhead issues are not a problem, make for sure that you've got, that's just a question of how far you want to get your men off the ground or your labor force off the ground to work with headers and so forth. So the insertion method must be appropriate. If you're dealing with structural concrete rehabilitation, you're probably just dealing with a rotohammer. Or if you're dealing with geotechnical work, you're probably dealing with sizable drills. But in any case, you got to realize that these probes can be inserted anywhere in the 360-degree spectrum, and you need to accommodate that. The annulus space needs to be limited on most casings and probes, unless maybe you're doing trim-tube work where you want the grout to come up that annulus space. But most of the time you want that that probe or that casing to have a tight fit to the whatever it is you're grouting through. When we look at monitoring, obviously the old gauges with clipboard and logging has been around the longest, but in today's world, computer monitoring you're going to find that more and more in a lot of your specifications coming up. Well, packers, if you're going to be around the grouting industry very long, you're going to be dealing with packers, and they come in all sizes, different types, but the two basic type are either a mechanical or an inflatable type packer, and they come in all sizes. Finally, we look at sleeve pipe injections, the system, and due to the length of time that we have here, I don't have a lot of time to explain just exactly, if you're not familiar with a sleeve pipe, how it works. But the nice thing about a sleeve pipe injection system is that once it's in place, you can do multiple injections over periods of time, and allows you to go back and take care of windows or areas that you didn't get the water cut off. You can do re-injections, and a very excellent system to do that type of work with. So with that, I'm going to turn it back over to Brian, and he's going to talk to us about some real-world applications.
Great. Thanks again, Sam. I've been asked to talk about some real-world applications of cementitious grouting. As we learned in the beginning, there are two major categories of grouting. That's the geotechnical and the soil stabilization, or the fracture and microfracture repair, or the structural part of that. Here's a couple of recognizable but not necessarily highly advertised projects where the geotechnical grouting resolves some very serious soil issues. Portions of these two stadiums were settling, and the underlying soil needed to be reinforced and stabilized. This was accomplished through successful permeation grouting. In both of these projects, we needed the grout to be able to effectively permeate the soils beneath the structure for stabilization purposes, and in some areas even needed to lift and restore the structure to its original position. That was quite a large project there. Here's another example of a similar use. The LAX Hollywood Metro Tunnel was settling in various sections. A highly skilled team of experts were able to use grouting to restore these problem sections to their original elevation, while securing and strengthening the surrounding soils to prevent future settling from occurring. This was a very complex project that required dozens of laser monitors to ensure that the surrounding buildings were not disturbed. One well-known application of structural grouting took place in the waste isolation pilot plant located near southern New Mexico. In their efforts to contain hazardous nuclear waste, the Department of Energy commissioned Sandia National Laboratories to seal up tiny microfractures found in the walls of the salt caverns deep beneath the ground surface where they were storing uranium waste. This was successfully accomplished by drilling ports and pumping ultrafine cementitious grout into the cavern walls. The grout was able to penetrate these microfractures, and according to the scientists at Sandia Labs who developed the grout, it will effectively seal them for thousands of years to come. While at the WIP site, we were trying to keep the hazardous waste contained within the caverns. Here at the Lake Mead project, the objective was to seal the microfractures to prevent water from the lake above from penetrating the tunnel processing going on during below. This was accomplished by boring several portholes about 80 feet ahead of the tunnel's path. You can see these port injector tubes right there. And then they would grout the section about 80 foot ahead. Once that cured, they would backtrack and position the explosives at the 40-foot mark and blow the charges. They would then clean out to where the new tunnel face had been established and repeat the process. By moving forward in this manner, they were able to seal ahead with a grout curtain of the blasting process and prevent the water from entering the tunnel. But I don't know that you could pay me enough money to get in a tunnel underneath that lake. And finally, we have an example of an ongoing grouting project at an active salt mine just outside of Minneapolis, Minnesota. The purpose of this grouting is very similar to that of the Lake Mead intake tunnel, but it is a continuous in that as the miners extend the existing tunnels forward during the mining process, it is critical for them to be able to grout and effectively seal off any newly exposed surfaces that show signs of microfracturing. I'll now hand this back to Britt, and he can cover some real-world applications of chemical and cementitious grouts.
Thank you, Brian. Moving on to chemical grout applications, one of the first projects we'd like to showcase, this is a tunnel boring machine project that occurred in Houston. The project consisted of installing a 72-inch sanitary sewer trunk line, which required a 96-inch borehole that was being installed using a micro tunneling machine. What happened, they anticipated the material, or what was expected is the soils that they were to be drilling through, or tunneling through, excuse me, were to be homogeneous, but they encountered a layer of material that actually softened. And when they did that, it caused the tunneling boring machine to pitch up slightly. In order to counteract that, they came through and injected through the face of the machine chemical grout to strengthen that material to allow the TBM to get back on alignment and successfully finish the project. Another project we'd like to showcase is Oak Ridge, Tennessee's Oak Ridge, Tennessee project. This is a hazardous waste encapsulation. Here they encapsulated approximately 9.5 million gallons of hazardous waste. What had happened was underground water was migrating through the hazardous waste and carrying it to local streams. The government went through and did a 20-year study on the different types of grouts that they wanted to use and concluded that an acrylamide chemical grout was the one to use. You can see here that there are multiple injection points throughout the entire trench that was encapsulated. One of the unique things here was the gel time set for this was approximately 8 hours. So they pumped for approximately 8 hours until the material encapsulated and gelled in place. Another project that has been a great success and ongoing for about 15 years now is the Toronto Subway, or TTC. This was a water control project where Toronto, obviously, like any underground structure, has encountered water leakage over time, and they've combated that by the use of chemical grouts and encapsulating that tunnel. They're so efficient at it that they've self-performed the work, both the drilling crews as well as the injection crews. They've designated their own internal rail cars for their pumping systems, and it's been very successful. Moving on now, a question we get a lot is, are cements and chemicals competitive, or do they complement each other? And our answer to that is they complement. Oftentimes, there are projects that require both cement and chemical grouts. Each have their own unique characteristics that are designed and engineered for, and oftentimes can complement each other. And here's an example of that. Dearborn, Michigan. This is a sanitary sewer overflow tank, and from this picture, see if it's in perspective, this is 120 feet in diameter across. These walls are approximately 7 feet thick, and this is approximately 150 feet in depth. What they determined was, prior to construction, there was an artesian situation with high water pressures that wouldn't have allowed them to construct it. The solution was to come in and pre-excavation grout around the perimeter of the planned location, using both cementitious grout to fill the larger voids, and then to capture the finer voids in the matrix porosity in the geology, if you will, with chemical grout. And you can see here that they were able to successfully grout very close with both cementitious and a chemical grout to a waterway, and ended up being a very successful project, nearly eliminating all of the inflow, or reducing the inflow to almost a negligible amount to allow for construction. Another project, this is a mine application. This is a bulkhead where both chemical and cement were used. Within the chemical family, there was polyurethane foams along with a chemical or a solution grout, if you will, or chemically reactive. This bulkhead was leaking over time. The leak was so severe that it actually flooded the mine. They came in and, like before, tackled the larger voids with the cementitious grouts and the finer matrix porosity with the chemical grouts, the chemically reactive, and then used the polyurethane foams to also seal up any voids in and around the bulkhead, and was very successful. Moving on to a project again where both cement and chemicals were used. This is a limestone mine where water flow was a big challenge. Like what Brian explained earlier, this was a grout and blast configuration. This slope needed to transition down through a water-bearing zone, and because of the matrix porosity, wasn't really able to take, wasn't able to be successfully grouted with just cement. So they used both cement and chemically reactive gel. They would inject upwards to 80 feet in front of the face in an umbrella pattern around the slope, and then come in and blast approximately 40 feet and repeat that process to walk down through the slope. It was very successful as well. Here's an example where they've excavated through or blasted through of some of the gel that's filled one of this little pocket, if you will. Moving on to a coal mine project in Illinois, same challenge, sedimentary type bedrock, slope had to go down through water-bearing zones, again, cement and chemical, not competing but complementary. This particular project was unique in that they did all of the mixing at the surface and pumped it down to this staging or this agitation plant, if you will, and then pumped it into the face of the structure or the face of the slope. Again, the same blast grout configuration, if you will, but a very successful and very happy owner at the end of this project.
Very good. I will take over the presentation on this, Britt. Thank you very much. And I've got already have a number of questions that's come across the wire, and they're good ones. And guys, I'll fire those at you in a moment. But before we start the Q&A process, and by the way, if there's any other questions to come in, now would be an excellent time. But permit me to highlight something that we deem very important. In the announcements leading up to this live learning event, we itemized 5 takeaways that you would yield from this presentation. Above all else, I want to make certain that we delivered on this promise. So when we started, Sam opened up our minds, I guess, to discuss what's possible with cement and chemical grout. Then Brian differentiated Portland cements over ultrafine, as well as slag over pozzum-based cement grout. Then Britt demonstrated some of the critical attributes of chemical grout. Sam came back, touched on technologies and methods for conveying grout, and Brian and Britt both talked about real-world examples of each grout type, and of course Britt highlighted projects where both are required. I'm going to start the Q&A process, and I will do my best to direct this to people I think are best able to answer it. One question that came in I thought was very interesting. Timber cribs, rock-filled, for bridge abutments or dams, can their lifespan be extended through grouting? And that's a question maybe that Sam could best answer, because I don't think it's dependent on chemical or cement.
Well, yeah, Don. Yeah, when you look at timber cribs, obviously you're dealing with wood structures. What you're looking at is your lateral forces, and if you can minimize those lateral forces from your soils by grouting, absolutely. And then also somewhat helping to extend the life of that wood. Obviously, wood only deteriorates as it goes through a wet-dry cycle. So if you can keep water away from some of those timbers, that would be very helpful. And so whether you do it with cement, you do it with chemicals, I would, yes, I've done a lot of projects like that. Britt, do you have any further comment in that regard?
Yeah, I agree with what you say, Sam, that absolutely, in my mind, that would be, a timber crib that's backfilled with gravel. If we can lock that gravel together, because obviously it's acting as a mass already in a mechanically stabilized earth retaining type wall or timber crib. As you lose that fascia due to weathering, if we can lock in that gravel and maintain that mass effect, if you will, that truly is the retaining area, the retaining factor in the component, that I do believe that you could extend the life of that component. You may lose the fascia with time, but that could be an easy fix, potentially maybe with shotcrete or some other finish. But the locking of the mass, I think, definitely is an opportunity to be able to extend the life of that system.
Next question. Unless you've got more to add to that, Sam.
Well, I was just going to say, in my experiences of working with cribbing and so forth, you're dealing with grouts that you're going to have a very fast set time when you're dealing with the face, because it's going to want to run through the cracks and so forth. So you're probably looking at a fast setting grout. If you're going to use a cementitious grouts, either adding a sodium silicate double injection system or using some of these chemical grouts where you can get the set times down rather quickly to try to minimize the loss of grout.
All right, this next question is about filling voids. Is there a requirement to flush voids prior to grouting voids or cracks? Is there a requirement to flush these voids prior to grouting or grouting voids or cracks? And I think that might be another Sam question.
Well, it depends on whether you're dealing with concrete structures or whether you're dealing with rock. But when you're dealing with dams and you're doing dam grouting, usually you're doing a water test before you ever do the grouting. So in that case, you've kind of flushed the joints just with the water testing system and to get your Lujan values and so forth. But if you're dealing with concrete structures, yes, I always recommend that you flush those joints out just to clean them, get any debris out of them that you can. And I found that to be very advantageous, if for no other reason than to just make for sure that all those intricacies are wetted so that they can accept the grout.
If there's no other comments on that, I'll ask Brian a question real quick, and this is centered around cementitious grout. How is it packaged, and where is it produced?
Well, we produce it here in the States, in southeastern Idaho. Our particular grout is packaged in 44-pound bags. It also comes in 2,000-pound super sacks. And we can custom package, as I'm sure most grout suppliers are willing to do. So.
I think I've got this next question squared away for you. Are urethane grouts used more frequently than chemical reactive grouts in projects? Take the ones we've done here in this presentation. These are more chemical grouts. But talk to me about urethane grouts. How often are they used and how are they different?
Is that a general question, I guess, all project types and scopes? I guess I'll address it according
yes.
to
Since
that.
we're talking about grouting 101 here.
Yeah. From a volume basis, in geotechnical type projects, a larger scale, generally we see that the chemical solution grouts are used more frequently on a higher volume, if you will. But if we're looking at crack injection, it just depends on the project. If we're looking at crack injection for a dam, for a tunnel where they're looking for water control as an existing structure, or sanitary sewer, manhole, storm sewer type applications, below ground infrastructure, polyurethane foams or polyurethanes get used frequently. So I see projects that are strictly nothing but polyurethane foams, and we see projects that are strictly nothing but ultrafine or a combination of the three. I guess my answer to that question is it's equal, and it just depends on the end user and the specifier and their desire of what product they think will fit the application.
Next question is for Brian. Are pumice and slag-based cement grouts the same?
Chemically, they are not the same. The slag-based obviously comes from a byproduct of the steel milling process in most circumstances. So you have a byproduct being used that comes through the melting process. It's kind of the foam if you will, that comes off of the molten steel. And then as it cools, then it's processed and crushed down to a usable size. Pumice is more, it's a natural pozzolan, or a natural product. It's mined out of a deposit and then processed to the correct particle size and processed into the grout. So they have some similar qualities, but they are chemically different, and they do have some physical properties that differ quite a bit depending on the application.
Good. You guys are answering pretty crisp answers here, and I appreciate that. Sam, here's one that you mentioned earlier, that there were 3 levels of grouting applications. What were those again, and why do you differentiate them?
Well, there's the homeowner, the commercial, and the industrial applications, and it's almost impossible for any one contractor or entity to handle all 3 levels. The reason being is the homeowner level, you're dealing with almost a commando type grouting application where you go in, you deal with a front porch, a patio, a driveway. You're in and out of there quite quickly. But when you get up into the commercial, certainly into the industrial, the contracts, the bonding, the insurance, the paperwork that's involved almost requires a full-time staff to handle all that. So the overhead and just the inventory that they must maintain to handle some of these industrial projects is just eliminates them from competing with the homeowner market. And certainly the homeowner market guys, you know, they're just not staffed, probably don't have the bonding capabilities and so forth to do some of these upper level projects. So they're, you know, the commercial side of it is kind of the transition point. That's kind of where you get the homeowner market coming up into that, but you get the industrial guys coming down into that. So that's kind of your transition area.
So what's that mean for the public works marketplace that might be tuned in right now? Most of our attendees right now are from the municipal marketplace.
Well, you'll find most of your commercial applications in that area. One of the problems you have with that type of an application is they try to pre-engineer the application. And I'm a real advocate, if you read my paper, of doing a design build, because when you're looking at risk, you run into a real problem when you get into the specified or engineered applications. That's not to say the engineer does not play a critical role. The engineer's job is to identify the owner's issues, make for sure that those issues are well known, well specified, and then let the contractor tell you how they're going to go about getting that end result for that owner, and the engineer is there to verify that that end result has been accomplished. But when you start specifying means and methods, then the risk factor gets thrown onto that engineer. If I jump through all that engineer's hoops and the end result's not there, that's not my fault as an applicator. But on the other hand, as an applicator, if I tell you I'm going to be able to shut that water off, or I'm going to be able to give you your end result requirements, and I go out there and do it and it's not there, the owner doesn't owe you anything. So my paper deals with you know, risk issues and so forth. So I hope that kind of helps, but typically you're looking at commercial applications there.
Gotcha. I have read the paper you're talking about, Sam, and it's a good one, and I know everybody on this call who's attending will receive that paper, and I encourage you to read it and review it.
Good.
Britt, I have time for one more question, and thank you everybody for being diligent on your presentation today and keeping us timely. Britt, you had mentioned a trial and error process when using various grouts and their associated costs. Could you explain what you mean by that?
Sure, thank you. What I meant by that was oftentimes, like Sam talks about, there's several geotechnical type projects that will be pre-engineered and predetermine what type of grout they anticipate based on the soils that they know are in place. But sometimes water will rear its ugly head and invade itself into a project that wasn't anticipated. And that point in time, then it becomes a trial and error process to determine which grout is needed to use in order to shut the water down or to achieve the goal. And oftentimes, the trial and error process will start with Portland cement because it's a standard, least expensive option. If the geology won't accept that, then the next step, oftentimes the contractor and owner will decide to move on to a cementitious grout, like an ultrafine, and frequently we'll have success with that. But if the geology then is so tight, with like a matrix porosity type geology, then a chemical grout may be the only solution, or a combination of both ultrafine and chemical grout. And so that's the trial and error basis that we see often that occurs as well, is Portland cement first, then cementitious, and then a chemical grout.
Well said, Britt. I'm going to take a moment here to launch one more quick poll question, and I'll ask those still on the call to respond if you could. We just try to figure out how we can best serve you going forward. Detailed information on cement grout or chemical grout, or continuing the education process. We're certainly in favor of that. And I got about a third of the votes in. Thank you for participating in this. Yeah, they're coming in slower because it's a little more.
Well, Don, while they're doing that, can we maybe talk a little bit about the grouting course that we just held at the Colorado School of Mines? Was well attended, and we had a lot of attendees from Canada and BC Hydro, a lot of the engineering firms, contractors from Canada. It was great to have them there, and a well-attended course this year. And I might just say, anyone that's interested, that course is usually held either the second or third week in June, and if you're interested and need the website or whatever, email me or just get in touch with us. We'll make sure you get the website to be able to sign up for next year's course.
Next year will be year 35, is that right?
That's correct. 35 years and running, and the course seems to get stronger every year. But I might also add, there are other ways to get involved with the grouting industry. The Geo Institute has a grouting committee. ACI has a grouting committee. ICRI. So there's a lot of committees out there that could use the help and experience of engineers, contractors, suppliers, and so there's just a lot of ways to get involved with the grouting industry out here.
Very good. As promised, there will be 3 documents shared to each of you who participated in this event. And these documents are well worth reading. This is the one that we've referenced from Sam. This is a project that Britt had talked about. And this is a nice synopsis of the presentation you just saw. Here's a small little quote-unquote commercial for Colorado School of Mines, which is a nonprofit organization, and Sam is a great leader in that process, in that educational service.
Good.
Sam, Brian, and Britt, if you offer a few moments of exit statements, I appreciate it. Go ahead. Sam?
Well, I'll start. It's just been my privilege to be a part of this webinar, and obviously the grouting industry has just been a great source of work for me over the years. I certainly appreciate the opportunities that it's brought, and being able to bring other contractors on board. It's just a myriad of opportunities out there, whether on the local level or international level. And the grouting industry is a great industry to be a part of.
And Brian?
Well, thanks, Don. I appreciate you inviting me to participate in this webinar. It's been great to work with you and Sam and Britt. Appreciate not only participating, but what I've learned as well. Hopefully this has been as beneficial to those who participated in this webinar today, and if we can do anything to help out, please contact us.
And Britt, if you would, please.
I would thank you. I resonate what both Brian and Sam have said about my appreciation to be able to participate in this webinar and look forward to assisting everyone with any of the grout challenges or questions that they may have, and appreciate the opportunity. Thank you.
I think we're all here to serve. Look, folks, we love teaching what we know and believe about cement and chemical grouting, and the only thing we like better than webinars is teaching nose to nose and belly to belly. And there's plenty of hands-on training opportunities here at Avanti's headquarters in Webster, Texas. We're just south of Houston, and you're encouraged to go to AvantiGrout.com to view additional educational options. As you exit this webinar, you'll be asked a few questions, and if you feel you were well served over this last hour, let us know. We fully intend to be the best in the business in these live learning events, and your feedback will tell us how. So, until the next time, I'll just say thank you and say so long.